come up. Welcome, good morning, by the way. I know this is early, but I appreciate you coming out. Um, and a few questions that came up over email. The first was number 6 on fall 23. I've actually had a couple students ask me about this in my office. Um, Y'all like these questions, don't you? Like we have a series of Yes, you mean? Yes, okay. A series of statements, and you have to know which ones are true. A box slides towards you. So it has a velocity in that direction, and you're over here, and you stop it. So you're applying a force to stop it. And the first question is, does the energy of the box change? Well, yeah, sure. So it has kinetic energy over here, and over here the energy, it doesn't have any energy at all. So that's true. That the energy of the box has changed. So by the way, I can get rid of those two, right? I apply a conservative force to the box. Anytime there are touching forces, contact forces, those are not conservative, right? Contact forces do not conserve energy. So I can get rid of 2, that gets rid of C. Oh, and that gets rid of E too. So I can say that it's 1 and 4, definitely. But let's look at number 3 as well. Did I do positive work on the box? No, because I'm applying a force in this direction, but the displacement of the box as it's coming towards me is to the right. So that's negative work. So it's not 3. And then this one, this is the one that people are getting hung up on. Did I cause the box to accelerate? And they said that can't be right, but it is right. If I'd written decelerate, and y'all would have said, oh yeah, that's a correct statement. But remember that accelerate doesn't mean necessarily to speed up, that it can mean to slow down. So in this case, it has a positive velocity, it has a negative acceleration. That means that the velocity is going to be decreasing. Accelerate just means to change velocity, not mean to speed up. All right, so that one is correct again. Another question somebody had asked about on that same exam is number 9. This is fall 23. Yeah, that's the next chapter. So this number 9 is chapter 6. They were confused about the equation. That's why. So we're going to get that next. We'll just try that today, actually, on momentum. And then I had one for number 4 in fall 2020. They said, hope you're doing well. I am doing well. I do have a question for more help session number 2020. Okay, that's this one. Number 4. Why do we set KE equal FD? Okay, these come up a lot, and you're going to see one similar to this on the quiz, of course, because, they're on every exam. So if they're not on every exam, then you're likely going to see it on the quiz, and on the exam, too, by the way. So I have this cardboard box. It has a speed. That means it has kinetic energy. As it moves across the floor, it has a velocity of 2 meters per second. So the velocity as it moves across there is 2 meters per second. And the type of energy that it has, well, because it has that speed, it has kinetic energy. So it has a certain amount of kinetic energy. But I want to know how far does it slide before it comes to rest. So at some point over here, the kinetic energy will all be gone. And the reason that it's all gone, because over this distance, it encounters a frictional force that acts over a distance d. And the work that's done by that frictional force, which is F times d, that work takes away all the energy from that object, this box that has a certain speed and mass. So all the kinetic energy that this box has is taken away by the work done by friction. That means that the kinetic energy that it starts with has to equal to the work that is done by the frictional force. Now you do need to remember a little bit from chapter 4, and that is that the force is equal to mu times the normal force. Make sure you remember that. It's chapter 4, but it's not on the equation sheet, so just make sure you know that. And y'all have different quizzes based on your section, but I'm pretty sure that comes up on both quizzes. Also, I don't know the normal force, but I do know the weight of this object. The weight, which is m times g, is 30 newtons. That means because this is on a horizontal surface, that the normal force is also 30 newtons. So I get a coefficient of 0.2, coefficient of kinetic friction, times my normal force of 30. So that is a frictional force of 6 newtons. Then go back now. Kinetic energy is 1/2 mv squared. The work done is going to be F, that's 6 newtons, times the distance, which is what I want to know. And I solved that for D. And put our other numbers in. 1/2 of 3, that's the mass. The speed is 2 squared divided by 6 is equal to D. So 3 times 4 is 12, half of 6. So D is 1 meter. D should be the right answer for number 4. Okay? You'll see a question like that on the quiz. So let me just make sure it's clear. This object has a certain amount of kinetic energy. It's taken away as it slides across this, the work done by friction. So I know that the kinetic energy is equal to the work done by friction. But along the way, I also have to determine the frictional force, which means I also have to find the normal force. The normal force, horizontal surface, no other forces. The normal force is equal to the weight. Yeah.
Is that the only equation with the last chapter?
Yeah, I mean, you have to know F equals ma or F equals mg. We had to use that along the way. You also had to know, this isn't an equation, but you had to know how to find the normal force. But I'm not going to give you a real complicated normal force. Flat surface, it would be equal to the weight. You might see an inclined plane, but in that case, you won't have to find the normal force. We'll probably see one of those questions like that. All right, I think I have one other question. Work number 7 from fall 2020. Was this fall 2020? Yeah. Okay. This just the way that it's phrased is a little bit different. I have 2 trailers, X with mass 500 and Y with mass 2,000. They're being pulled at the same speed. So they have the same speed. So they only differ by their masses. So the ratio of X to Y is 500 to 2,000. And I want to know what is the ratio of the kinetic energy of Y to that of X. I want to know the ratio of the kinetic energy of Y to X. That's going to be the same ratio. The kinetic energy is 1/2 mv squared. Kinetic energy is directly proportional to the mass. So it's going to have the same ratio. That would be 2,000 to 500. I flip it because I'm asking for the ratio of Y to X. That's 2,000 over 500, which is going to be a 4-to-1 ratio. You might have been inclined to say that it's a 1-to-4 ratio if you just gotten it flipped, but that's not an option. I don't like that question. I got to write that question. I pulled that from some other source, so you're not going to see that question. Okay? Y'all hear that on the video? Not gonna see that question. So, not a question I would pull for the quiz, but one that you should. I mean, I think you know how to do it. It's just sort of strange language, but common standardized test language, ratios in that way. All right, are there particular questions that y'all want to talk about? That was all, yeah.
Like number 10, please.
Yeah, of course. Yeah, you're going to see a spring question. We've done some of these. The ones that we did in class, I don't think we've done one like this. Ones that we did in class started out where I have some elastic potential energy, like I'm shooting a spring-loaded gun, and then all that potential energy goes into kinetic energy. This one is similar. What you want to do is I have some object that has only potential energy, and it falls onto a spring. And so I know that the gravitational potential energy will all be converted into elastic potential energy. I'll do that right here in the middle. So PEG will equal to PES. That's MGH equals 1/2 kx squared. MGH is 1.5 times 10, so 15 newtons. That's mg. I just did this times 10. times 2 meters is equal to 1/2 of K of 150,000 newtons per meter. And then I need to know what x is. So it's 30 divided by 75,000 square root. That gives me a distance of point x is equal to 0.02 meters. That's not an option, right? But that's not what I'm looking for. I'm not looking for a compression of the scale. I'm instead asking, what does the scale read? And so I need to take a second step, which is that F is equal to Kx. K here is 150,000. Yeah, that's right, times 0.02. 300,000. 3,000? Yeah, 3,000. That's going to be 3,000 newtons. So 2 steps there. In other problems, I might just ask, what is the compression? But there was an additional step where once you find the compression of the spring setting our gravitational equal to our elastic potential. Once you find that x, then you use Hooke's law to determine what is the force that's being read on that scale. I mean, that's what scales do. They have a spring in them, and they're calibrated so that when you compress the spring by a certain amount, it reads some force. Okay, so yes, possible. I did pull a spring question. I don't know if I pulled that, but I did pull a couple spring questions. Other particular questions? You're going to see conservation of energy, the sort of roller coaster problem like we did in class. You'll see spring questions like this. You'll see work energy questions. Let's do that. That's not the one I'm looking for. An inclined plane problem. I think those are more recent. Now holler out if you have specific ones you want to see. Oh, let's do this one. I'm not saying this is on the quiz, but there are some similar ones like this. Here I have a block that's sliding down an inclined plane. Notice that the length of that inclined plane is going to be 5 meters. It's a 3, 4, 5 triangle. If you don't remember that, you can do the square root of 3 squared plus 4 squared. That's equal to 5. 9 plus 16 is 25. There's a frictional force, says, that is equal to 10 newtons acting on this block. And I want to know what happens, what's the speed when it reaches the bottom. So up here it has potential energy. Down here it has kinetic energy. If there were no friction, I would just set those two equal. Potential equals kinetic, and then I would solve for the speed. But along the way, there's work that's done by friction that's equal to F times D, where D is the length of the incline. It's not the horizontal length, it's the length of the incline. Be careful with that, not 4, it's going to be 5. So that potential energy is mgh. The work done by friction is F times D. I'm subtracting that because that energy is taken away. And then all that's left will be our kinetic energy, 1/2 mv squared. So I can solve that. I have 20 times 10 times 3 minus 10 times 5 equals 1/2 of 20 times v squared. So 200, 600 minus 50, 550, 55, I think 7.7, must be 7.7. No, I get 7.4. I'm sorry, 7.4. Okay? There are other types of questions like that. Let's look at this number 8 while we're here, since I like these so much. What outside surgery and you stop it, which of these statements is true? So sometimes, like on tests, I'll just take the previous question and I'll just sort of change the statements. So you might see something like that. Do they do negative work on the box? Don't stop it? Yeah. It doesn't take an energy away from it. is the work I did equal to the work of the frictional force? Not necessarily. Like maybe, but not. It has to be always true. The gravitational force did work on the box? No, no. Because there's no vertical displacement, there's no work done by the gravitational force, and I did positive work on the box. So here we get yes, that's correct. That gets rid of those. The work that no, not correct. That gets rid of that one. And no, not correct. That gets rid of that one. And that one's not correct either. Okay. Other particular questions? No? Yeah.
Should we do the spring problem?
Yeah, of course. Let's just see if, I think there's one here. Yeah, here's one. This was a little simpler than the one you asked about, Blaze. That one was a little more complicated than usual. But that doesn't mean that you won't see it on the quiz. Number 4 here, I have this block. It's traveling horizontally at a speed of 4 meters per second. That means that it has kinetic energy. So I know I'm starting with something with kinetic energy, and then it runs into this spring. It comes to rest. That means that all of its energy is converted into elastic potential energy. So that's my framework. I'm converting my kinetic energy into elastic potential energy, and then I'm looking for x. So I have 1/2 mv squared equals 1/2 kx squared. Get rid of the halves. M is 2, v is 4, k is 2, and I want to know what x is. X is the square root of 4 squared, so x is 4 meters. Okay. That one was simpler, quite a bit simpler. Let's see if we can see another one. Might be more complex. Oh, can we do, actually, let's do this roller coaster problem, because you'll see one similar to this. Roller coaster has a mass of 200 kilograms and a speed of 10 meters per second. Listen, I know that, I don't think all of them we've done have been this way, but you might be inclined to say that it just has potential energy up here because you missed this little point, that it also has a speed at the top. So it has potential energy and it has kinetic energy. Just be really careful to read all the text. And as you're reading it, just sort of make notes along the way. It's important, okay? All the text is important. It goes down the slope. The height at point A is 30 meters. What is the speed at point B? I know at the bottom here it only has kinetic energy. So that would be, I would set those two equal. PE plus KE equals KE at point B. This is at A. So that's going to be, I'm just going to go ahead and get rid of all the M's. I know that they cancel out. So that's going to be GH 10 times H, which is 30, plus 1/2 of V squared. That's 10 meters per second squared, equals 1/2 of V squared. Y'all see what I did? I didn't write the M's because I knew they were all going to cancel out here. It's 350. V is equal to the square root of 700. Is that 24, 26? I don't know what that is. $26. All right. Looking for another spring question. Okay, this one is similar. Let's look for another one that's different. Okay, this one's a little bit different. Well, no, it's all the same. You want to do this one? Is that okay? The spring? Are y'all other particular questions you want to do? Anything particular? What you got? Huh? Number 9? Yeah, is that okay? All right, so I have a spring-loaded gun. It shoots. It has elastic potential energy here. It says that the compression is, well, I don't know what the compression is. I want to know what that is. And then in the final state, it stretches out, and then it gives this a certain speed. So it has kinetic energy over here. So I'm setting those two equal. I'm saying that PES equals the kinetic energy. It's going to be 1/2 kx squared equals 1/2 mv squared. Those halves can go away. I'm looking for x. So I'm going to solve that for x. The square root of mv squared over k. You can put in the numbers if you want, if that's easier for you. That's going to be m was 0.02 times v is 30 squared divided by k, which was 250. It's the square root of 0.072. You get 0.268 meters, which is 27 centimeters. That's 0.27 meters. I expressed it in centimeters. Just move it over to this one. Let's see, we did that one. Make sure you know the expression for power, and then also make sure you know how to do the units. I'm pretty sure there's a question like that. That shouldn't be a big surprise. Let's look at number 13. There were several problems in the exams and past exams where I'm just asking you what is the total work. The total work is just the sum of the forces. So here I have, bless you. Huh. I'm going to skip 13. Let's see what's the answer here. Sorry, y'all. Let me look. I don't think I see a mistake in it. Was there a mistake in that one? Do y'all know? That was 13. B. Anybody see? Was there a mistake in the video? Y'all see it? Okay, let's see. So I want to know the total work done on the block. I showed two forces here, the 20 and the 5. And so a simple way of doing this, which would be wrong, but I'm going to show you. I'll explain to you why it's wrong. I'm pretty sure that's what I did in this one. Is to say that since I'm moving up the inclined plane, the 20 Newton force does positive work. That's 20 times 2. That's positive because it's in the same direction as displacement. And then the frictional force does negative work. That's 5 times 2. And so that's 100 minus 10, or 90 newtons. So that would, not 90 newtons, 90 joules. That's not right. I'm sorry. 40 minus 10, 30 joules. Yeah, that was the answer. But that's wrong. There's actually another force that's acting, that's doing work on the object. Do you know what force that is? Yeah, both. No, not the normal force, because the normal force, yeah, the weight. The normal force is perpendicular to the motion, so it's not doing any. But the weight, a component of the weight, is doing work. And so it actually does do some amount of work. I'll need to take that off. So you're not going to see this. Y'all see what I'm saying? That there's another force that's doing work without it. Sorry about that. I could have said what is the work done by those two forces, but I think I put that on the quiz. I'll take it off. All right, I'll take it off. Not on the quiz.
No, would number 14 be on the quiz?
No. I won't take you to those. Let me make a note of that. What exam was that? That was 2020. And 14. Oh man, I printed them already. I'll print them again. Oops. All right, other particular questions? Y'all feel ready for the quiz? Huh? 70%? That's what you're going for?
No, ready.
Oh, you're ready. 70% ready. Okay. Yeah, don't go for 70%. Go for 100%. All right. Let's do this one. This one is just a little bit different. We didn't do any graphs, but I think that y'all could figure it out. The total work done by the boy on the wagon as he pushes it across this distance of 4 meters. So he goes a distance of 4 meters. That's D. And the force, I mean, you're just really reading the force off of here, that he has a force of 30 newtons. So it's just going to be 30 times 4, or 120 newtons. Yeah, that's all. Or if you wanted, you could be fancy and find the area under that graph. The area under a force times distance graph is the work done, right? Because it's just the force times the distance. Y'all know the SI units for work? Yeah. Caitlin? Yeah. Oh yeah, I'm surprised nobody's asked about this. So I have this car that moves across two paths. It has a short path, and then it has a longer path. The fact that they go through different ups and downs is almost irrelevant, like that one goes lower than the other. But at the end, they both end at the same height. So if there's no friction, then they should have the same velocity when they get to the end. But it says here that it does experience a frictional force, so I know that the car is going to be traveling slower after going down the longer path. Because on the longer path, it loses more energy due to the frictional force. So let's see, the velocity of the car traveling path A is larger. No, that's the opposite of what I just said. Oh, I'm sorry, no, that is true, actually. I'm sorry. So A is the right answer. B is actually going slower, and they don't have the same final speed. Okay? Is that clear why that is? Okay, good. It comes up in other questions. The longer the path, the more energy you lose due to the frictional force or any non-conservative force, any contact force. Other questions, Joe? Okay. Let me stop this.